Hi, in this video we're going to look at the maths submissions test from 2018 for Oxford, Imperial and Warwick. We've got as far as question 6 here, which is, as you can see, for computer science, maths and computer science and philosophy applicants. So although you didn't do this one if you're applying just for maths or maths and statistics, actually it's still very good practice. The questions tend to still be very mathematical, but perhaps have a little bit more, have a sort of procedural or algorithmic thinking element to them. So please don't forget to like the video, to subscribe to the channel if you're finding these useful, share them with your friends who are applying for this as well. Loads of other content at the website that's linked below and at my Amazon store also linked below if you want to have a look at those. But let's get on with this question, and it says a positive rational number q is expressed in friendly form if it's written as a finite sum of reciprocals of distinct positive integers. For example, 4/5 is equal to 1/2 plus 1/4 plus 1/20, and it then wants us to express these following numbers in friendly form. Now, before we start, just focus really carefully on the definition here. It's got to be a finite sum, so fairly obvious, just finitely many terms in it here. We can't have like a limit of an infinite sequence. But just be careful about the rest of it. It's a reciprocal of distinct positive integers, so I must have positive numbers on the bottom here, so I've just got to be adding things together. Reciprocal, so it's always 1 over those integers, so 1 over a whole number, can't be any other type of fraction. And this word is going to turn out to be important, distinct. If we're asked to show something about these numbers, we're going to have to make sure that we've shown clearly that the numbers that we've got are different. Okay, so can't repeat any of the fractions. So first part really just to help you get to grips with the what's going on in this question. So we've got to just try and express these numbers in this form, and if you just start playing around with it, it shouldn't be too hard. There are different ways you can do these. There's not just one right answer here, but in general I guess I'm going to try and take a fairly large chunk out of the number here first, and so I will say, right, here let's just do 2/3 is equal to, maybe this one's fairly obvious, you can just do 1/2 plus 1/6, or if you try out a number here, you would just work out 2/3 minus 1/2 and find that it's 1/6. Similarly for 2/5, now I can't take a half here because that's bigger than 2/5, but I could still take a third, and so if I do 2/5 minus 1/3, that gives me 6 minus 5 over 15, which is 1 over 15, and so we see actually that we're done straight away here. I get 2/5 is 1/3 plus 1/15, and for the last part, 23 over 40. This time again I can clearly take out a half, which is 20/40, and that leaves me with 3/40, and then at that stage perhaps you just notice that you can write 3/40 as 2/40 plus 1/40, so I get a half plus 1/20 plus 1/40, or if you wanted to keep going with this, taking the largest possible number out of it, you know, you could also do that and say, okay, 40 divided by 3 is like 13 and between 13 and 14, so the point is that 1/13 is too big, 1/14 is the next one you could take out, so you could also write the 3/40 as 1/14, and if you work out 3/40 minus 1/14, you find that that is, I've checked this earlier, 1 over 280, so that would also be a possibility. You could write it as a half plus a 14th plus 280th. So here's part 2. And the rest of this question is really going to be about showing that we can do this in general for any fraction. And there's an interesting bit of maths behind this really. These are actually called Egyptian fractions. It might be something you've come across before perhaps if you've done some reading of kind of recreational maths books. You don't need to have any prior experience of them, but that's what we're aiming towards here, representation for kind of any fraction in this form as a friendly number. So part 2, it says let q be a rational number with 0 less than q is less than 1. So we're just starting by looking at rational numbers that are between 0 and 1, and let m be the smallest natural number such that 1 over m is less than or equal to q. If you think about it, this is kind of what we were doing in some parts of the previous question here. It's saying, okay, if I take the smallest number for the denominator, that gives us the largest possible fraction that I can subtract from the fraction q that I'm looking at here, right? So q could have been 2/3 or 2/5, and then here m would have been 2 and m would have been 3. Okay, and now it's saying, okay, so let's write q in its sort of rational form with natural numbers here in their lowest terms, a and b, and see what happens when we subtract off that number, as I was doing in the first part, from q to give a new rational number c over d in its lowest terms. And what we want to do in this part is just to show that what we end up with c here is smaller than the number we end up with a here, which is what we got here, right? If I started with a numerator of this fraction, I ended up with something smaller in the new numerator once I'd simplified it. Similarly here, 23 became 3, and if I follow this procedure as I did in the green ones here, then it becomes 1. So I get this decreasing sequence of numerators, and that will turn out to be very useful. But one step at a time, so let's follow the instructions that we've been given. So I need to investigate this thing, I think, q minus 1 over m, and q, of course, I can write as a over b, so that's a over b minus 1 over m, and I could combine this into a single fraction now. I'm really here, see, just repeating what I've been doing in question 1, but in general, if you're wondering why I'm starting to do this, where I'm taking my rational number, subtracting this 1 over m, and then sort of simplifying it into a single fraction, I get here a times m minus b divided by b times m, and this is equal to c over d. Okay, so actually what I need to do is to show that this numerator is smaller than a. We should just think very quickly about this being in its lowest terms, and you might make a quick comment here, I'm not going to write it out, that actually this fraction may not be in its lowest terms, okay, but certainly this number c has to be certainly smaller than or equal to am minus b, because basically either this is in its lowest terms, or if either b or m cancel from the top here, then c would be smaller once it's cancelled down. Okay, so that's not going to turn out to affect our conclusions here, but it's an important detail just to check. So actually, what do I need? I would need that I really want to find that am minus b is less than a, and if I just rearrange this, this is am minus a is less than b, so that's a times m minus 1 is less than b, and I can write that as saying that I need that a divided by b here is less than 1 over m minus 1, and remember a over b is q, so that q is less than 1 over m minus 1. And now this is true because m was the smallest natural number, such that 1 over m was less than or equal to q, so it must actually be the case then that 1 over m minus 1 is larger, because, you know, by definition we chose m to be the smallest possible thing that made this work, so m minus 1 must not make it work. So actually, if I wanted to, now, okay, this is a good example actually of how you might answer an exam question here. I've done some logic here that's kind of got me to the, I can see the logic now, but what I really want to do is to now reverse this logic. So if I'd written this in my exam paper, I might now actually say, rewrite this out in the other order, right? So say, okay, now q is less than 1 over m minus 1 because of this, and then actually work my way back up these statements. I'm not going to write them all out again here, but just rewrite this argument in the other order so that I get that am minus b is less than a. Again, and by my argument here then, that means that c is less than or equal to am minus b is less than a, and then I'm done. I've got that c is less than a. Okay, so the way I've written out here would not get you full marks in this exam. I want to really reiterate that. The logic is there, but you do need to kind of reorder this and incorporate how I've said this into the way you write it down. It doesn't take much here, you just need to write it in the other order and then come to the conclusion at the end. Okay, so that's part 2 done. And this procedure is going to turn out to be useful. Okay, so it says in part 3, suggest a procedure by which any rational q can be expressed in friendly form, and use the result in part 2 to show that the procedure always works, generating distinct reciprocals and finishing within a finite time. So again, one of these things that's important for computer science, that when you write a computer program, that you do something algorithmic, it's not going to just keep running forever. So the fact that we've got a finite number of terms in this friendly form means that, say, if I were to write this as a computer program, that program would terminate in finite time. Okay, so what are we going to do? Well, effectively, we're going to employ this algorithm. We're going to take the largest number possible, the largest reciprocal of a natural number, away from our original rational number, and then just keep doing that until this terminates. And that's going to work because, as we saw, these numerators are getting smaller every time. So this numerator must start as some number. Every step it's going to reduce and reduce and reduce, and so it can only be finitely many steps until the c in our fraction here is equal to 1. Okay, so I just need to write that down somehow, and this time let me try and write this out a little bit. So we're going to start by choosing m to be the smallest natural number m, such that 1 over m is less than or equal to q. Okay, and then we're going to evaluate q minus 1 over m, which is c over d, and this giving a rational number with c is less than a, which is what we've got by part 2. Okay, so now I might say define q1 then to be c over d, and repeat. Okay, so and you don't have to be totally rigorous here, but you might just say, okay, so I get q1 minus 1 over m1 is maybe equal to e over f, and I'm going to define that. This colon equals means defined to be equal to q2, where now with e is going to be less than c, etc. Now continuing, so we need to say something like continuing this gives q1, q2, which are rational numbers whose numerators are decreasing. Okay, I guess I could say positive rational numbers whose numerators are decreasing, hence after finitely many steps a numerator will be 1. Okay, and the algorithm will terminate. So I'm going to say something like that. Now, there is, if you've been paying careful attention here, one thing that we haven't checked, which is if you think back to the definition in part 1, right, or before part 1, it says we had to have distinct positive integers, and I said that we must be careful to check that definition. Okay, so let me just write the end part up here. So I might say, moreover, these. Now this is the handy thing about introducing a bit of notation as you go along here. What I've defined as m1 here, right? Moreover, m1, m2, etc. are all distinct. And why are they distinct? Well, it's because, in fact, they must be a sequence of fractions that are getting smaller, i.e. values of m that are getting larger, because if m1 is not larger than m, okay, sorry about my handwriting here, because, for example, if m1 is smaller than m, okay, we could have chosen m1 instead of m at the previous step. Okay, so the m1, m2, etc. is actually a strictly increasing sequence. Okay, so actually, so we've got that as well. Okay, sorry about my handwriting here; it's not too easy to write on this tablet sometimes. But hopefully that all makes sense, and you can see the sort of argument that you're meant to write out here to give. Answers here don't have to be, super long. They've just got to be rigorous and correct. And, tick off every point. Okay, so it says part 4, demonstrate your procedure by finding a friendly form for 4/13. Well, okay, now this time I really do have to work out what the largest fractions here are, and if you're not sure, I guess one way would be to actually do division or something, right? If I worked out 13/4, okay, this is a bit silly really, but I'd get 3 point something. Okay, so so that means I can't take out 1/3, it's too big, but I could take out 1/4. Okay, so I've got 1/4 as my first step, and on the side here maybe I'm going to just work out what 4/13 minus 1/4 here is. That's 16 minus 13 over 13 times 4 is 52. Okay, so that's 3/52, which doesn't simplify down, but it means I get 1/4 here plus 3/52, and we see, as we did before in the first part, this numerator is decreasing, and then now 3/52 again. Well, 51 is 3 times 17, so again 52/3 is 17 and a bit, so the next best one I can take out is 1/18. Perhaps on the side here let's do 3/52 minus 1/18, and so if you just work that out, I'm sure you can do the fractions, you get 1 divided by 468, and thankfully the procedure has terminated there. Okay, so it's really just asking you, I think, I'm not sure how much it matters about how you show you're working here, just making sure that you get the friendly form here that is achievable by always taking the largest possible denominator at each step. Right, okay, part 5 then actually generalizes this result just a little bit further, and it says, okay, now assume that this sum, which you might know as the harmonic series, increases without bound as n becomes large. I've actually done another video a couple of years ago at least now that proves that this is the case, proves that this harmonic series is infinite. It's a very, very important example in real analysis, but we're allowed to just assume that's true, so show that every positive rational number can be expressed in friendly form. Okay, so let's just take now let q be a positive rational number. So in fact what I'm going to do here is I'm going to write that as n plus let's say n plus a over b, okay, where n is a natural number, right? So 1, 2, 3, 4, etc. I guess I could also include 0 in my natural numbers here. Okay, so just for completeness, okay, so let's say the natural numbers include 0, and a over b is going to be between 0 and 1, so effectively this is, I'm writing, if I've got a rational number, like let's say it was 3 2/3, I'm writing it effectively as 3 plus 2/3. Now this was my, actually, I've just realised that I've written this was actually my first way of thinking about this problem that turned out not to work very well. But given I've got this far, this is quite, to me this seems like quite a natural thing to do. I sort of thought, well, okay, maybe if I could just write the natural number as sums of terms from the harmonic series, right? Which I know I can do because this increases without bound, so I can definitely get n as a sum of fractions. Now I have to, but you see, even then it's a little bit tricky because I'm not sure exactly. I've still got to specify exactly how to do that, and I'm not. Although it's clear that this series exceeds n, I'm not sure exactly when it does. It's actually a little bit awkward. But then I could also do this a over b in friendly form, and I could add those together. But then I've also got a problem that I don't know if the numbers I've used in here and the numbers I've used in here are distinct, right, in my friendly forms. So actually, this is quite a sensible way of starting, I think, but turns out to be a bit awkward. So what we're going to do here is actually to effectively take this harmonic series just as far as we can, taking the first terms, right? So let's say I'm trying to get to. Okay, let's not make it too big here. Let's say I'm trying to do 9 over 5 or something. Right. What I'm going to do is I'm going to say, okay, let's take 1 over 1 plus 1 over 2. That gets me to 1 and gets me to 1.5. Now, if I took 1 over 3, that would take me to 1 and 5, 6. Actually, that takes me a little bit beyond 9/5, because that would be 1.8, wouldn't it? And this would be like 1.83 or something if you want to do it in decimal. So actually, I'm not going to take that one. I'm just going to take these, right? But the idea is I would take as many as I needed to in order until I get as close as I can to this number, right? So to write that out, what I'm going to do is say let k be the maximum natural number such that the sum from n equals 1 to k of 1 divided by n is less than or equal to to q. Okay, so I'm calling I suppose I should say, okay, let q be any positive rational number, so that's our target as it was before. Okay, so what I get here is that sequence that doesn't, if it gets to q exactly, that's great. I might just manage it by chance. If I did 3 over 2, it would just be 1 plus a half and I'm done. So what I'll say then is, okay, if so assuming, so let's say, okay, so if equal to q, then we're done. Okay, otherwise we're going to let q prime be the difference between these, so q minus the sum from n equals 1 to k of 1 over n plus 1, and necessarily this must be smaller than 1 over k plus 1, because if it wasn't, I could have added it in to my sequence, right? So in my previous one I did 1 plus a half and I couldn't quite get a third in there, so it must be that what's left is smaller than the next fraction in the list that I didn't include. Okay. Now we know that since we've got 0 is less than so 0 is less than q primed is less than 1 over k plus 1, and in particular 1 over k plus 1 is less than 1. Okay, so hence by the previous part it was part 3. Right, q primed, and it's also a rational number obviously, so I should say that q primed is also a rational number here. I guess that's obvious, but hence by 3 q primed is expressible in friendly form. Okay, and moreover, all of the fractions in this friendly form will be 1 over values here. Let's just give it another name. So let's say 1 over p, where p is larger than k plus 1, because, I mean, my whole q primed is smaller than 1 over k plus 1, so I can't use any any fractions that are bigger than that. So so all are distinct from those used in the sum from n equals 1 to k of 1 over n. Oh, sorry, I put in a plus 1 here. I just realised in this fraction that shouldn't be there. Obviously, it should be 1 over n here. I was getting ahead of myself and just getting ready to write 1 over k plus 1, I think. So in particular, I've used some fractions in this part of the harmonic series. I'm looking for a friendly form of something that's smaller than any of the ones I've already used. So as I split it up into other fractions, those must be smaller than ones I've already used. So again, I get that important condition satisfied that the fractions are distinct. Okay. Okay, so that's it. So we're done. Hence, hence Q has been represented in friendly form. Okay, good. So so interesting bit of maths here. In fact, if you want to know more about these, it's a very interesting topic. You can go to Wikipedia here and look up Egyptian fractions. You can see an Egyptian fraction is just what they've called friendly form here. So there is certainly an advantage in doing lots of recreational maths to prepare for your application, not just for the fun of it, but also because I guess people writing these papers have to draw their inspiration from somewhere. Notice I've pulled this one out of the Wikipedia page as well. Notice it doesn't always terminate quite as neatly as the one examples we've got here. If you start with 5 over 121 and you follow the algorithm that we've done here, always taking the largest possible denominator at each step, you end up with something pretty horrific. Although this isn't the only way to do it, so there are easier friendly forms or Egyptian fraction representations of this number, just not using that algorithm there, which we'd perhaps call something like a greedy algorithm. Anyway, that's enough for this video. Everything for this whole paper is in a playlist, so do watch the rest of those. Let me know if you've got any questions. Don't forget to like the video, subscribe to the channel, and share this with anyone else that you know that's taking the paper. Good luck with the exam, and I will see you for the final part of this paper, which I will upload as soon as I can.